Hi, so I'm Casey. I was super excited to find out that one of the themes this year was going to be complexity, because that's something I study at London University in a human factors and safety systems program. So I love the topic, and one of the things that I'm most excited about are things that we take for granted, things that feel intuitive that actually aren't true. So hopefully I can address some of those. Does this? No? Okay, this works. Okay. Which brings me to American culture. So this is going to sound really pretentious, but I bet some of you have been to high school. And in high school, you probably had an American Lit class, if you studied here in the States, and you probably read some typical stuff like Steinbeck or Longfellow or Hawthorne or maybe some Mark Twain. Why do we do that? Well, so the reason that you read those things is that you can kind of get a sense of what society was dealing with at that time, get a better sense of people at that time, and hopefully understand our culture better. So one of the things I like to think about is, assuming that humans are still alive in 100 years, what will high school students in the former United States study to learn about us? And I would argue that they won't be studying literature, they'll be looking at movies. And the genre that's dominated the past 2 decades of movies are superhero flicks. And I just find this fascinating, because you can actually see changes in time through our culture by how the superhero genre has changed. For example, Superman of the late 30s, 40s, and 50s. Superman doesn't really work as a movie anymore. His catchphrase was truth, justice, and the American way. And that just doesn't resonate with the majority of the audience for these movies. So what does? Well, so Marvel had 4 big blockbusters in 2018. In 2 of them, the hero was a terrible person, Deadpool 2 and Venom. They were anti-heroes. And in the other 2, Black Panther and Avengers, Infinity War, they actually spent more time on the villain. There was more character development for Killmonger and Thanos than there was for the good guys. Why is that? Why are we focused on anti-heroes? Why do we flirt with this notion that it's better to tear everything down, burn everything to the ground in order to save it? And it's not just in media. You might be able to see some of this in politics, maybe, on the left and on the right. And not just here in the States, Brazil, in the soon-to-be former Europe. So back to software. Why is our industry so focused on disruption? Why do we think about how great it would be to just burn everything down and use that as a place to start over? So I propose that the reason that we focus on that, the reason we flirt with that idea, the reason it's appealing, is because at some fundamental gut level, we know that the way the current system is wrong. And that applies to the software too. The way that software currently rewards behavior and evaluates work and delivers value day to day, at some level we feel that that's wrong. So let's get back to software here. So complex systems. So put that thought on hold and let that tickle the back of your brain while I talk about complex systems. I love putting this picture up because it shows microservice architecture, the spheres are microservices, the moving dots are requests from Netflix's critical path. And just at a really high level, this shows that no human can understand how this entire system works. We'll take that as the definition of a complex system. When you've got a mental model of how stuff works, but no one human can understand how all of these parts fit together, which means you can't really make super predictive statements about changing one thing down here is going to affect something way over there. In this example, internet traffic is coming in from the left and fanning out through the microservice architecture. What could go wrong? So fortunately, Laura gave us a bunch of great examples of things that could go wrong. I want to focus on one really quick. So here, imagine this is a zoomed in on a microservice architecture. And we'll say that microservice P stores data about people, personalization data. It manipulates it, adds some metadata, but it doesn't actually persist stuff. So it passes that off to Q, which does the persisting. But that's also a stateless microservice. So it stores things, it coordinates the storage in, let's just say, Cassandra, and it also stores stuff in Redis. And when you read stuff out, so P will store people, it never deletes them, it's really simple. But then when it reads stuff out, same thing. It'll read it from the cache first, but good engineers. So we've got logical fallbacks in here. If Q can't reach the cache, then it'll read it from Cassandra. And if for some reason it can't talk to both, then it'll return a reasonable response, a default response to P. And the same with P. It has logical fallbacks. So if for some reason it gets an error from Q or can't talk to Q, it has some default personalization data that it'll return. So then one day Redis says, Mr. Stark, I'm not feeling so good, and stops responding. So in a situation like this, often when you have a read cache like this, it means that you have a read-heavy workload. So unfortunately, Cassandra, it can handle all of the writes, and you kind of have an idea that it can handle that traffic, but the cache actually hides how much traffic Cassandra can actually handle. So unbeknownst to the operators, Cassandra can't actually handle this read workload. So eventually it slows down and stops responding. But we've got the fallback. So Q says, OK, I can't talk to either of these. It'll return a default response. And in this version of Cassandra, when you can't form a quorum, it'll return a 404. So Q returns a 404 to P, and P says, WTF, we never delete people. So it crashes and burns and takes the whole system down with it. Now what I love about this example is who screwed up? What went wrong? The answer is, obviously we know what went wrong, but nobody screwed up. The engineers actually went the extra step. Most engineers don't go through the step of creating these logical fallbacks. They did a great job. And yet we get this aberrant behavior, this behavior we don't want out of the system. So this is a misalignment between application logic on the Q side and business logic on the P side. And there's no reason that you could expect humans of either of these teams to sit in a room and close the door and say, OK, in 1 hour I want you to think of everything that could go wrong, and then we can create a plan to solve it. You can't have, people can't think of things that they wouldn't have thought of. So that's just not a reasonable thing to do. So this is a problem with complex systems. So how do we fix it? In a complex system, all components could be 100% correct, and yet the system exhibits undesirable behavior. How do we survive the undesirable effects of complex systems? Or to put it simpler, since this is SREcon, how do we make systems reliable? Usually when I ask people in a more intimate setting, the first thing I get back is, well, redundancy. So software engineering is basically rocket science. So let's talk about rocket science for a second. This is a picture of Challenger, 1986, taking off, which is a great case study to study from the point of view of resilience engineering, or looking at big engineering failures. Why is it so important? Well, so during the height of the Cold War, the US held a competition to find America's teacher. And she was going to be the first non-astronaut civilian to go into space. Actually, the second, but the first was a politician, so nobody cares. And so in '86, in January, because she was a teacher, they were going to live stream this and live stream a lesson from her into a lot of schools. So some of us are old enough to remember when the Challenger exploded, we were in school, and the teachers, with tears in their eyes, had to try to explain what we had just inadvertently witnessed. So there were congressional hearings, there were a lot of books written about this, about what went wrong. Very, very briefly, I'll talk about some of the engineering parts that went wrong. So that rocket that was closest to you in the picture, a solid fuel rocket, is actually made up of components that fit together. They slot together, they're assembled on the field, and to seal them together, there's two O-rings, a primary. Here's what an O-ring looks like. So you can see it in the cross-section here a little bit better. There's two O-rings that make that joint super sealed. Here's a better close-up. And then they cover that with putty to protect it from heat. So after the shuttle goes up, the rocket falls in the ocean, NASA retrieves it, analyzes it to see how it performed. And by the second shuttle run in the early 80s, they had noticed that there was heat damage to the primary O-ring, which was a little bit troublesome. So they spent months and for the better part of a year, made changes to the formula of the asbestos silicone putty that they put on top of that. But changing that formula introduced air bubbles, which still allowed heat to get through. So it wasn't consistent, but every once in a while they would still find heat damage on that primary O-ring. And in the next year, they found a little bit more damage on some of them. And so they tried things like inserting a needle between the two and putting some air pressure in when they were testing it to make sure that it sealed properly. But they used too much air pressure, so sometimes that created more air bubbles. So they had to modify that over the course of a year. And then in '84, they saw finally some evidence that some hot air had actually gotten past the primary O-ring. And so then they looked at, okay, changing the design to put more pressure around the outside to hold that seal together. And then in '85, they saw heat damage to the secondary O-ring. And so they redoubled their efforts to bring that new engineering plan to fruition. Unfortunately, in January, early '86, heat made it all the way past the secondary O-ring, burned both O-rings, and that's what caused the engine to fly out back into the rocket, and the whole thing exploded. Best engineers, this was the pinnacle of American engineering, right? So who screwed up? Well, it's the same as the previous example. Nobody screwed up. Everybody was doing their best job, and they had hundreds of potential safety issues that they reviewed for each launch. They had institutionalized the process of delaying shuttles. So more shuttle launches were delayed than not. So it's not that they were afraid to delay it if they thought there was a safety concern, but they had a lot of process in place, and they decided that it was okay for this shuttle to fly. Why? First of all, because the functionality had redundancy. There were two O-rings, when really it should have only needed one. The deviation is within the experience base. So they saw some damage, the shuttle went up, the shuttle came back safely. So clearly, it was safe. Works on my machine. And they thought the issue was self-limiting. If the pressure pushes the O-ring in, it'll make a tighter seal. So like maybe some other part of the system will actually compensate for this defect. So now the interesting thing to note here is that if there had only been one O-ring, then the shuttle would have been stopped after the second mission. The fact that it had the redundancy actually allowed the process to continue, which ultimately led to the failure. And I have many stories where redundancy has actually contributed to the failure. So redundancy doesn't solve these problems. So again, back to the question, how do we make systems reliable? What else can we look at? Avoiding risk. So this is very intuitive, right? Like, let's make our systems safer and like put guardrails up so that people can't really do the dangerous things. So I've got this great study from Squirrel Academia. If you've never looked into it, Squirrel Academia is fascinating. It's a little nuts, but there's really great research that comes out of it. So squirrels divided themselves into two groups. Those that travel a lot, go far from their home, and cross a lot of streets. And another group that's a little bit more sedentary, like stays at home, right? Stays very close to home, but still crosses some streets. And they looked at the automobile mortality rate for these two groups of their species. And what they found when they wrote up the paper, the research, was really fascinating. It turns out that the squirrels that crossed more streets, that took more risks, got dusted less often by cars. So the squirrels that crossed fewer streets actually had more car accidents, more fatal car accidents. What does that teach us? It teaches us that exposure to risk is actually a fundamental part of us learning how to handle and mitigate and remediate risk. So if you as engineers aren't exposed to it, then you're going to perform poorly when you are eventually exposed to it. So you need to be exposed to risk in order to do a better job. And guardrails prevent that. They also prevent you from having degrees of adaptive capacity, the ability to improvise in the moment in order to save a system. So avoiding risk backfires. And of course, the research fortunately made its way up the animal chain and finally did us, and we eventually replicated these studies with humans too. So that's great. So here's the solution. Simplicity. Take the complexity out of your complex system, right? Then it's a simple system. Sort of, not really. That's actually 100% wrong. So you can put complexity into two buckets very simply. One is accidental, okay? So accidental complexity is the complexity that gets added just from writing code, just from you going through like the process of doing your job. You're going to accidentally add some complexity. And so that's always increasing, just like dirt, comes into your house by accident. I've got 3 little kids, so they bring it in on purpose, but presumably you don't. So dirt accidentally accumulates. Same with complexity. The interesting thing about accidental complexity is that while you can stop what you're doing and clean it up, there's no sustainable method to do your job because you're not paid to remove complexity, you're paid to add features. There's no sustainable method or discipline to remove accidental complexity or lessen it. At best, you can kind of keep it even, but in practice, that rarely happens. So this is always going to increase. The other group is essential complexity, complexity that you put into the system on purpose. Now, why would you do this? Well, let me give you an example. Imagine that you have the simplest data store that you can imagine. KV runs in memory. You give it a key and a value, it stores the value. You give it just a key, it'll return the value. Running on your laptop. And the business says, that's great, that's exactly what we need, but you know what? The database disappears every time you close the laptop lid, so let's make it more available. Okay, how do we make this more available? Well, let's put it in the cloud, right? Okay, that's an easy one. What else can we do to make it available? Let's put it behind a consistent hash so that we've got multiple nodes that replicate the data. Okay, we know how to do that. It's a well-known thing in data systems. What else can we do? Well, we can replicate that to multiple data centers or regions around the world. Again, very well-known. In less than 60 seconds, I traversed like this well-known but complex path of adding availability to your data store. Let's go back to a simple example. Now imagine, on my very futuristic-looking laptop here, imagine that management, the business said, okay, the requirements are make this database more available and simpler. Ready, go. You can't do it. It's impossible. In fact, adding features, adding complexity, that tracks with the success of your software. So if you say, I want to reduce the complexity in my software, what you're actually saying is that I want to reduce the ability for me to be successful. And your business probably doesn't want to do that. So you got to go in the opposite direction. You don't increase complexity on purpose, because why would you increase anything for the sake of it on purpose? But you allow the complexity to develop, and instead of getting rid of it, you have to learn how to navigate it. How do we make systems reliable? So how do we navigate this complexity? Here's one model. This comes from Rasmussen, and it basically says that implicitly, as engineers, we're all operating with 3 invisible boundaries around us. One is economic, workload, and safety. So economic, right? If you generally know how much you cost, how much your team costs, how much your resources cost, and you know that if you run out of money, you're dead. You go to business, you're dusted. Same with workload. You get too busy, your machines get too busy, right? You cross that line and you're dusted. And then safety, right? If you run in an unsafe mode and an availability accident happens, so here's the problem. You have an intuitive sense of economics, you have an intuitive sense of workload. You have no intuitive sense of how safe your systems are. And I'm comfortable projecting that on most of you because you still have incidents, right? Availability and security incidents. And if you have them, it's not because you don't take your job seriously, it's because you didn't know it was coming. Otherwise you would have stopped and fixed it so that it didn't happen. So you have no intuitive sense of where that safety margin is, which is where chaos engineering comes in. So I built and managed the chaos team at Netflix, and we sat down and wrote the definition. And we designed it to be a proactive discipline to teach you where the safety margin is. A little bit more formula. The facilitation of experiments to uncover systemic weaknesses. So it teaches you about the weaknesses in your own system. And an important note here, all the other practices that we generally talk about, everything from incident management to observability to disaster recovery to monitoring and alerting and paging, those are all reactive. All necessary, but all reactive. They're time to detect and time to remediate. So chaos engineering was designed to be proactive. It tells you ahead of time and helps you develop this intuition about how safe your system is. So that's one thing that you can do. What else can you do to make your systems more reliable? So this model, another one I'm a fan of, the economic pillars of complexity. I stole it from Kent Beck, but it's okay. He stole it from an economics professor. So economic pillars of complexity says there's 4 pillars that you can adjust. The states, relationships, environment, and reversibility of your product or manufacturing or maintenance process. The quintessential example here is Ford from the 1930s, 1940s. You can have any kind of car that you want as long as it's a black Model T. So they severely limited the number of states of their product. And they also adopted assembly line manufacturing. So they limited the number of configurations that the whole process could have. And then they also limited the number of relationships that you could have in the manufacturing process. Other car companies had a team that built a whole car. But implementing Taylorism, you can maybe talk to the person to your right, probably not the person to your left. So it was very super simplified. Ford couldn't do much to impact their environment. And reversibility is really hard. It's hard to unmake a car. I'm not talking about putting a car in reverse, obviously. So how does this apply to software? Well, your business probably has an imperative to increase the number of states. You're adding features, so you can't really control that. And relationships, well, we're going to microservice architectures. Just look at all of the different layers that we have now. Kubernetes adds another layer on top of that. So the number of relationships in the components increases. And companies are probably growing. Can't really do much to change the environment unless you're monopoly, Amazon. But reversibility. Here's where software engineering has a distinct advantage. Starting with the revolution with XP over waterfall design, getting the process of building software into chunks that you can easily reverse decisions. And that was process, but now we have it in products. Right, like feature flagging and blue-green deployments and the CI/CD tool sets. And containers, you can get your code into production and then reverse that decision much easier. And what I love about this is you can apply this heuristic as hopefully you have a say in the architectural decisions that you make to actually deliver code. And so you can say, when you're at a fork and you say, okay, we can go this way or that way, you can actually say, which of these solutions gives us something that's more reversible? Because the more reversible solution will pay dividends down the road in navigating a complex system. Okay? So we can favor reversibility, and that gives us a competitive advantage. What else can we do to make systems reliable? So here's my favorite. The chief merit of software engineering is its technical efficiency with a premium placed on precision, speed, expert control, continuity, discretion, and optimal returns on input. Sounds right? That's our field. Except I oopsed. The actual quote is, that's the chief merit of bureaucracy. Oh, now the heads are shaking the other way. Software engineering, the bureaucratic profession. This is what sociologists call us. Why are they so mean to us? That sounds terrible, right? Nobody wants to be called bureaucratic. Why would they call us that? No other industry does a better job of separating who decides what work is going to be done from who decides how it's going to be done from the people actually doing it. That's, I hope, an uncomfortable giggle, because that describes most of the software industry. So getting back to the question I asked at the beginning, maybe you kind of have an uncomfortable, intuitive sense that software is all being done wrong, because most of it is. Why do we have that system? It's a holdover of Taylorism, where you have unskilled labor at the sharp end doing manual work, making widgets. Is that what we do? No. We're knowledge workers at the sharp end, navigating complex systems. That system of bureaucracy was designed for a completely different economic model and production model than what we're dealing with. So this will make a great, most of you, to about 2/3 of you are engineers. So this is a great topic for your next one-on-one with your manager. Tell me about your thoughts on bureaucracy and your place in it. And how do you as engineers think about who decides what work gets done? You're the one in the complex system with your hands in it, closest to the context. Shouldn't you be the one who decides how to build those solutions? So this is more what your work looks like. You've got many different factors that are simultaneously competing for your attention, and they're changing minute by minute with additional context that you get, which means that, given any design decision that you make, it's going to change moment to moment depending on the current situation that you're in. So you need the ability to improvise, which is like the antithesis of bureaucracy, in order to successfully make it through that kind of situation. And that's what will help make your system, your sociotechnical system, more reliable. So I call this the kitchen model of organization. Think of a well-run kitchen. Hopefully you've had the experience, I don't mean commercial, hopefully you've had the experience Thanksgiving or something, or just friends coming over, where like you participate in making dinner, or maybe even just like setting the table or whatever. But nobody there is going, okay, lift the knife, move the celery forward, put the knife down, lift the knife, move the celery forward, right? That's not what happens. It's really uncoordinated, and somehow dinner just ends up happening. It just gets done. And that's what you want to, that's what a reliable team looks like. That's what a reliable socio-technical system looks like. And so hopefully you've been in that experience, and you've also had this happen where you finish a task, and you look around, and all of a sudden, you're in everybody's way. Why is that? Well, it's because we have millions of years of evolution that allow us to model the behavior of the people around us subconsciously based on understanding what their goal is. And the minute that you're done with something, everybody around you no longer has a model of what your goal is. So you become an obstacle to them. Everybody was moving fluid, you're done with something, now you're an obstacle, because why are you there? So this is what you want to keep in mind when you're trying to figure out what should a team look like to create and maintain a reliable system. You want everybody to know what everybody else's goal is, and then just let them move where they need to move and improvise when they need to avoid, the knives flying through the air or whatever happens in a kitchen in order to get the job done. So here's my cheat sheet on how to make our systems reliable. Embrace complexity, navigate it. Don't try to remove complexity. Provide opportunities for teams to practice working together. This isn't training, this is practice working together. Helps them figure out how to communicate and move fluidly among each other. Tolerate inefficiencies. I love this one because as software engineer, being a software engineer, we're like, oh yes, efficiency, we need to be efficient. No, efficiency is brittle. If you want your system to be reliable, you need to have inefficiencies in there. Optimize for reversibility, and communicate the safety margin. Tools don't create reliability, humans do, although tools can help. I wrote a book on it, Chaos Engineering, with my team at Netflix, and I have no idea if we have time for questions. So what is that, like one question? We'll say one question. Okay. Two questions. I think you have to run up to the mic. I don't know.
Why do you have the Thanos flow?
Why do I have the Thanos gauntlet? The real question is, why don't you have one? Okay, maybe one more question. That was a really easy one. No? Okay, well then find me afterwards. Thanks, everybody.